The first thing that you're going to see is our basic interface, the default one. And for reference, up here, there are going to be some smooth curves that you see representing the predictions of the baseline model, which is most standard in epidemiology. They're called compartmental models. This is an SEIR model. And what that stands for is S is susceptible, that's the blue curve. E is exposed, that's people who have become exposed but they're still incubating. And then they become infectious, that's the red curve. And finally, they recover, and that's the green curve. So over time, by the 100th day or so, you see that a lot of the population has gone from being susceptible to actually one of the other states. So they become exposed and infected. And the numbers of people who are infected and exposed have been growing. And over time, eventually, most of the population in this prediction by day 200 or so, most of them have already been not only exposed and infected, but have recovered. So to start a run, what's going to happen is that we're going to create a population of individual agents. These are humans. And right now we've set it up so that there are 200 humans initially. 198 of them are susceptible. And initially, there are 2 infected ones. And those are, in this picture, the 2 red dots that you see over here. So another thing I'd like us to look at in this control over here is what are the mask characteristics. So the mask characteristics here say, on the one hand, I've set the slider so that it's 70% effective in terms of the mask transmission rate. So if I put on a mask, that says that when I am expelling, when I'm exhaling, the mask is only effective at stopping 70% of the droplets carrying the viruses from getting through. And that corresponds to the fact that we're talking about potentially even homemade masks, right? So we want to show you that wearing masks, it doesn't have to be those big fancy N95s. Even if we get everybody who's wearing masks to be wearing these masks that are 70% effective in terms of stopping your transmission, and also in terms of absorption, we'll assume that it's only 70% effective in stopping droplets carrying viruses on the way in. We're going to start letting simulations like this run. All of the dots are just going to start moving. Now, what we're seeing here is this population. You can see the clusters over here. They're growing. They're more and more orange and then red humans that are walking around. The infectious ones, the red ones, when they meet another susceptible human, they can infect them. And so you see how the infection is spreading. Up here, you see how this is actually reflected in the curves. So the blue curves have been showing a precipitous drop in the number of healthy, susceptible people. Meanwhile, we've had peaks in the infection. And one of the things about this style of agent-based modeling is that it has the advantage of showing you the amount of variance, the amount of random variance that really happens. Because every time we run this, we're going to get a different output, right? So these curves, they're similar in shape, but you can see the outcome here was actually quite a bit steeper drop in the number of healthy people than the simple curves predicted by the SEIR model. Right, and we're doing another run of the same type. And here you're seeing the curves. Again, it's following the same sort of shape, but you're going to see the variance. And every time you run it, you're going to see something different come out because of essentially things like butterfly effects, right? If this guy decides to cross the street that one day, he might infect someone who goes ahead and infects a whole bunch of new people and creates a new cluster of infections. And so those things tend to create large variations. But if you run this many times, you will find that it averages out to something which is similar to what the SEIR curves show. So you can see this one ends up in a very similar position to the SEIR curves. It's running a third time right now. And again, it's following the curves pretty similarly to the SEIR predictions, but it's going to show the variation representing the idiosyncrasies of the behavior of each individual agent. You can go ahead and play with this on your own and watch the variations. If you get impatient and you want to do a different run, you can click on the fast forward, skip buttons over here. You can also pause or stop and hit play to restart a new simulation. So let's go ahead and let's consider what happens when the population starts wearing masks, because that's what we're interested in here. So let's start a new run where the population is all wearing masks. I've gone ahead and set the slider down here to 100% of the population wearing masks. And so you can see, if you look closely here, all those little dots are now wearing little white masks. And look what happens to the curves, right? The masks are, even though we set those masks to be only 70% effective, meaning that they're only stopping 70% of the droplets from getting through in either direction for transmission or absorption. That is enough to significantly cut down on the rate of virus spread. And so this is super important because it's helping buy time for the hospitals, right? The peak of the red curve is much lower than before, so we don't overload the hospitals. And also it helps buy us time to develop treatment and vaccines and other things that are just going to take us still many months or a year or more to develop. So we're going to start another run now, and I've set the slider back down to 0. So initially the population is not wearing masks, but now on day 50, suddenly I move the slider to 90%. So this means that on day 50, we've got most of the population wearing masks. And look what happens to the curve. So the curve was, the blue curve was dropping precipitously, but once we mask the population, we sharply start arresting that spread, that rate of spread. And this means that even if we didn't start masking up everybody on the first day, by day 50, we still have a chance to significantly reduce the effects of the spread, the rate of spread, and to control that red curve to keep the load on the hospitals down. So now let's consider what happens if we mask everybody up at day 50-ish again. But let's say that it's not 90% of the population, it's only 50% of the population that have masked up. What happens in that case? So this is a very common scenario where, maybe that somebody has said, maybe the government has said, oh yeah, you can wear masks, but there's no real push for everybody to be wearing masks. And what you see is that on average, you do not have anywhere near as good a chance of containing that rate of spread. 50% of people being masked is just not enough to have a significant enough effect on the exponential rate of growth that this sort of infectious spread happens. This is why it's so important not just to encourage masking, but to encourage universal masking. We want 80% or more of the population wearing masks, even homemade masks, in order to make a difference significantly. And so here again, we've got a run where we started at 0 with nobody wearing masks, but instead of day 50, we wait until around day 75 to say that people should be wearing masks. Again, look what happens. If we don't move fast enough, not enough of the population is wearing masks in time to arrest that rate of spread. Again, on average, if you do many of these runs, you will observe that we really do not want to take the chances of waiting until day 75 or at day 50, getting people to wear masks, but only sort of half of the population is wearing masks. Neither one of those approaches is really good enough. We need, by day 50, to be getting people wearing masks universally, at least 80–90% of the population. They can be homemade masks, it's no problem. There are plenty of instructions that we can point you at to make your own homemade mask without a sewing machine that is just as effective as a surgical mask for protecting your community. Remember again, when we mask up, it's not so much to protect yourself as doing your part to help protect your community. And we need to all do that because ultimately we are all on the same boat.